Each year, humanity consumes
stretching from the wires inside our homes to plumbing systems and even massive power grids. Meeting this immense demand cannot rely on mining alone. The answer lies in copper recycling. Scrap is collected, carefully sorted, cleaned, melted, and refined to be reborn. Every cycle saves up to 80% of the energy compared to primary extraction, cuts millions of tons of CO2 emissions.
And remarkably, copper can repeat this process endlessly without losing its quality. Those olds around you,
serving once again as the backbone of modern civilization. In this video, we follow the extraordinary journey of copper's endless rebirth. Nearly 80% of all the copper ever mined throughout history is still in circulation today, proof that recycling is not just a complementary measure, but a cornerstone of the global supply. In the United States, about 1/3 of annual copper demand is met through recycled scrap. Collections span everything from old wiring and plumbing to discarded electronics and decommissioned infrastructure, all of which is refined in modern facilities
to produce pure copper, ready for every industry. The value of this process goes far beyond economics.
In the era of energy transition, America requires vast amounts of copper for smart grids, EV charging stations, wind turbines, and solar panels.
Recycled supply has become a true strategic buffer, reducing dependence on new mining while ensuring a steady flow of red metal, for the defining technologies of the 21st century.
When copper scrap arrives at collection yards, it is often piled into massive heaps or bundled into compact bales for easier handling.
These sites are not just temporary storage. They serve as the crucial gateway to the entire recycling chain. Here, we're
relying on skill and direct observation. Bright red copper, usually with higher purity, is set aside for greater valuation, while darker pieces coated in grease, wrapped in plastic, or mixed with steel are sent to different sections.
The distinction often comes down to subtle clues, color, surface shine, or even weight in the hand.
Yet the accuracy can determine the worth of an entire shipment. In a typical yard, about 60 to 70% of the volume is copper
that can be reused after basic cleaning, while the rest consists of alloys or contaminated material requiring deeper treatment. Organizing and separating on-site not only lowers refining costs later, but also ensures safe, compact storage, reducing fire risks.
From residual oil. In this way, copper scrap yards become a vital link, transforming chaotic collections into a stream of material with clear and measurable value. After sorting, scrap copper wires are fed directly, entire coils or bundles, into high-capacity shredders. These machines use rotating shafts lined with hardened steel blades, powerful enough to tear through both the plastic insulation and the copper core inside. As the bundles are pulled into the grinding chamber, they break apart into a mixture of fragments and fibers. Heavy copper pieces on one side, lighter, more fragile plastic on the other. The mixture then moves through multi-layer vibrating screens combined with air separators.
Under vibration, the dense copper granules drop to the lower levels, while lighter plastic fragments remain above
and are carried away by suction fans. In some facilities, magnetic conveyors are added to remove stray steel and iron mixed within the wires.
Thanks to this system, the initial mass is quickly transformed into 3 distinct streams:
clean copper, recyclable plastic, and other metallic residues. This approach makes it possible to handle huge volumes without the labor of manually stripping insulation.
In fact, each ton of scrap wire can yield 400 to 450 kilograms of pure copper,
with the rest consisting mainly of PVC or polyethylene. Importantly, the separated plastics are not wasted. Once cleaned and ground into fine pellets, they are reused in products such as pipes, liners, or new cable jackets.
By combining bulk shredding with precise separation, yards optimize processing speed and improve recovery efficiency.
An essential advantage when dealing with hundreds of tons of obsolete wiring each year. What once seemed like a chaotic mass is reshaped into clear resource streams.
Bright, high-value copper cores and industrial plastics ready for reuse.
Once freed from plastic and other impurities, copper scrap is fed into smelting furnaces. Most facilities rely on electric induction or arc furnaces, an essential advantage when dealing with hundreds of tons of obsolete wiring each year. What once seemed like a chaotic mass is reshaped into clear resource streams.
Inside the furnace, the scrap is heated together with small amounts of flux, which draws out remaining impurities and gathers them on the surface as slag.
This slag is continuously skimmed off, leaving the molten copper below in a purer state.
What makes this step remarkable is that melting does more than liquefy the metal. It effectively renews copper's life cycle. Each batch often blends materials from different orobins: electrical wires, brass shavings, and red copper recovered from old plumbing. By combining these inputs, the final composition can be tailored to demand, from high-purity copper for electrical conductors to specialized alloys.
For industrial manufacturing, energy consumption in recycling furnaces is typically only 1/5 of that required to mine and refine virgin ore.
Yet the efficiency remains just as high. A single melt can process dozens of tons of scrap,
transforming fragmented pieces into a continuous flow of glowing liquid metal, ready to be cast.
It is here that copper reaches a turning point, where discarded remnants complete their old cycle and are reborn.
Point as pure material for entirely new applications.
From the furnace, the stream of molten copper, glowing a deep orange-red at more than 1085 degrees Celsius,
is tapped into massive ladles and carried to the casting line. Here, precision molds await,
ready to shape the liquid metal into standardized forms. Depending on demand, the copper may be cast into long rods, thick slabs,
or cylindrical billets that will later be rolled, drawn, or machined into finished products. Continuous casting is the method most widely used.
The molten copper flows into a water-cooled mold, where its outer shell solidifies instantly, while the core remains fluid.
Complete the solidification, producing a continuous bar of copper that can stretch for dozens of meters before being cut into uniform lengths. This stage is critical because it determines the structural integrity of the entire batch. Controlled cooling prevents internal cracks
and ensures the grain structure remains consistent, giving the copper both strength and conductivity.
Each bar, slab, or billet is then marked for traceability, linking it back to the exact furnace batch it came from.
In just a few minutes, what was once a chaotic pile of scrap has been transformed into gleaming new blocks of industrial copper.
These casts are now the foundation, ready to be rolled into wires, pressed into sheets,
or alloyed for machinery, fueling the industries that rely on copper's unmatched versatility. Before moving on to the next stages, blister copper is reheated in specialized furnaces designed for uniform thermal treatment. This reheating process stabilizes the crystalline structure of the metal, drives out residual stresses left from solidification,
as the heat penetrates evenly, trapped gases and minor imperfections.
Toodles can also be reduced, ensuring greater consistency for the refining that follows. In the glow of the furnace, the giant copper slide into one that is softer and more workable. After reheating and cooling, the semi-pure blister copper slabs enter the decisive stage, electrolytic refining. In massive tanks stretching tens of meters long, filled with copper sulfate mixed with sulfuric acid.
The blister copper anodes are suspended alternately with thin, stainless steel cathode plates.
When a direct current is applied, copper atoms dissolve from the anode into the solution, then migrate and redeposit onto the cathode surface,
forming layers of copper that are nearly perfectly pure.
This process runs continuously for 7 to 10 days, and it reveals a fascinating phenomenon. Precious metals such as gold, silver, platinum, and selenium do not dissolve but instead settle at the bottom of the tank as what is called anode slime.
Far from waste, this byproduct becomes a valuable source of materials recovered for use in jewelry, electronics, and the chemical industry. The end result is flat, thin cathode sheets of copper with a purity of 99.99%, sufficient for even the most demanding applications in electronic and high-tech industries. Each sheet weighs around 80 to 100 kilograms and is typically stacked on pallets, sold on global markets almost like a metal currency. From these cathodes, copper begins its next transformation, drawn into wires, rolled into thin foils, pressed into electronic circuit boards,
or cast into industrial components. In some metallurgical plants, once the electrolytic refining process is complete,
pure copper cathodes can be packaged and shipped directly. These flat, thin sheets, each weighing between 80 and 100 kilograms, are stacked into large bundles, tightly strapped, and sold on the global market as a standardized international commodity. However, in most cases, cathodes leaving the refinery are remelted and cast into wire rods, cylindrical billets about 8 millimeters in diameter. This is the industry's standard intermediate form, bundled into massive coils weighing several tons, then shipped to wire production facilities around the world.
On the drawing lines, these coils of wire rod pass through a series of rolling stands and drawing dies.
Each pass reduces the cross-sectional area and elongates the strand, shrinking the diameter from 8 millimeters down to just 1
or even a few tenths of a millimeter for signal cables and microcircuit conductors. To prevent brittleness and cracking, the wire is continuously annealed,
preserving both ductility and high conductivity. Once the desired size is reached, the copper wire is coated with insulation, PVC, XLPE, or Teflon, depending on its intended application. Finally, the finished product is wound into
ready to power construction, utilities, transportation, and high-tech industries.
From the original cathode sheets, copper has completed its transformation into wire, the essential backbone of modern infrastructure.
In Korea, the craft of copperware has a history stretching back thousands of years, originating during the Three Kingdoms period.
As early as this time, Koreans had already learned to extract and smelt copper, casting it into temple bells, incense burners,
Buddha statues, and a wide range of ritual objects. Archaeological findings reveal not only the early advancement of metallurgy,
but also the deep connection between metalwork and the spiritual life of the people.
At the heart of this tradition stands Bangja Yugi, a unique forging technique regarded as a national secret.
Instead of casting once and finishing later, artisans melt a copper-tin alloy and pour it into a rough mold.
Then subject it to a repeated cycle of heating, hammering, and rolling by hand dozens of times. Each strike of the hammer not only shapes the vessel, but compresses its structure,
giving the final product exceptional durability, even heat distribution, and resistance to warping over long use.
As a result, Bangja bowls, spoons, pots, and trays are not only sturdy but also glow with a warm golden hue.
Cherished by Koreans as symbols of prosperity, purity, and harmony.
Today, although modern industry has largely replaced traditional household ware, Bangja Yugi remains recognized as a national intangible cultural heritage.
Korean families, especially during New Year and ancestral rituals, still favor Bangja dishes on ceremonial tables and formal meals.
Visitors. More than simple utensils, each piece carries spiritual significance, serving as a living link between the present and the tradition.
The journey of recycled copper is more than a series of technical steps. It is proof of how humanity has learned to give metal an endless life cycle.
From what once seemed like worthless scrap, copper can return to a pure state, retain its intrinsic value, and continue serving humanity in the most demanding fields.
That is why nearly 80% of all copper ever mined remains in circulation. A rarity in the world of materials, where most resources are quickly consumed or degraded in quality.
This shows that copper recycling is not just an economic advantage, but a strategic pillar.
As the world races toward renewable energy, electric vehicles, advanced infrastructure, and high technology, a sustainable supply of copper becomes vital. Every ton of recycled copper means less pressure on the Earth, less energy consumed, and fewer emissions released into the atmosphere.
It is the balance we need between progress and responsibility. Yet this cycle carries a fascinating truth.
The very atoms of copper powering today's cities may once have existed in ancient temple bells, tools, or weapons forged thousands of years ago.
Copper does not age like humans. It continually regenerates in new forms, from monuments of the past to microcircuits inside modern smartphones.
It is the lifeblood of our world, connecting past, present, and future.
This is why copper recycling stands as one of the clearest examples of the power of the circular economy.
Turning what was discarded into the foundation for a new cycle of growth.
Do you believe that the home you live in, the car you drive, or even the device in your hand may contain copper atoms mined thousands of years ago?
Share your thoughts in the comments, hit like, and subscribe to